So in this talk, I will introduce, as the title suggests, a structure of pre-length space to the set of all causal diamonds in our Lorentzian pre-length space. So why did we started looking at this kind of thing? Well, the main motivation was because as this theory is coming together, is evolving, we need examples, right? So our first motivation was to look for examples of Lorentzian pre-length spaces. So originally, most of the examples that we had were somehow linked or attached to general relativity. We had space-times with metrics that were not C2, or that had boundaries, or even some objects that arise naturally in a causal theoretical setting, like the causal completion, right? All of them come from here. But there are also a large class of examples that come in a more theoretical way, shall we say. So we can define cone structures or different kind of products, like word products, that carry on this structure of Lorentzian pre-length space. So, but going a little bit beyond that, we have like some very clever examples, like in the original paper of Kunstinger and Saman. We can find the funnels. They are cute examples. And also some examples that are typical, like in metric geometry, like this one, like in causal space with sticker. This is like a non-smooth extension. We have this kind of examples, and surprisingly, we have also examples that are completely detached. A priori, example of the context. So, the question is, how common is to find Lorentzian pre-length structures in mathematics that carry some geometrical meaning? We also had all these discrete examples of nets and graphs, other sets. So it appears that this structure arises in several different terms, right? So that was the motivation. We look for examples, right? So along with the motivation, there is an inspiration. So where do we look? Where do we look for these, shall we say, novel examples? Right? There are so many different aspects to this low regular geometry that, I mean, we have witnessed in the past couple of days this a nice interplay between various areas of analysis and also geometry, things like geometry. So where do we look at? Well, there's been some things that we have been exploring from the topological setting called hyperspaces. And since we had some handle on how do these things work, we decided to go after our examples in the setting of hyperspaces. So for topologists, hyperspace is just the family of subsets of a given space, right? So just to fix ideas, we can have a metric space. We look at all the compact subsets of that metric space. And there are some fundamental theorems that have been proven like in the 60s and 70s. This is one of them, due to Cortes and Shori, that describes topologically up to homeomorphism, how do they look? For instance, if I consider the class of all compact subsets of the real line endowed with the Hausdorff metric, I get that it is homeomorphic to the Hilbert cube, that is the countable product of closed interval with a point remove. And if I look at like at a compact example, instead of taking here the real line, I take closed interval. That will be very similar to this. It will be also the Hilbert cube. So the Hilbert cube appears as a model in these examples. By the way, there is nothing really particular about the choices of R or the closed interval. Here, it is basically enough to ask for something non-compact, and here for something compact. In most cases, we'll have this. As long as it is locally compact and connected, have this kind of behavior. And more recently, no homeomorphism. Homeomorphism. This is completely at a topological level. They are homomorphic. And very recently, Sergei Antonyan, in a couple of papers, he proved that now, if we look at the isometric classes given by the Gromov-Hausdorff metric of distance of all the compact subsets of R, it also has the same property. It's like this. And the same happens if we take, for instance. Actually, he proved even more. He proved this in full generality for Rn and the closed ball in dimensions. But I'm writing this just for dimension 1 because something really important for us to say that this is joint work with some colleagues in Yucatan from Valdemar Barrera and my student Luis Montes de Oca. So we've been studying this set, this hyperspace for quite a while. So this is the hyperspace of all closed intervals in the real line. So that's why I'm just looking at dimension 1, but this is proven in full generality. Okay. So in this case, the case that we were analyzing, we have this hyperspace. We consider the Gromov metric, the Hausdorff metric, and we want to explore this in a geometrical way. So before we do that, just a very quick interlude. Just a reminder of how this Gromov distance, well, actually Hausdorff distance works. This is Hausdorff. So whenever I have two sets of subsets of a given set, the Hausdorff distance between them is attained like this. It's the infimum of all the R's in which each one of them is contained in a tubular neighborhood of radius R or the other. So it is, if we ask a little more, if we ask for not just a metric space, but a locally compact complete length space, we have a bunch of properties. For instance, regarding the metric space itself, we have the existence of midpoints. Given 2 points, there always exists a point that realizes half the distance in them. The tubular neighborhoods, I say that closed tubular neighborhoods behave in a very nice way. They are compact, and if I take the tubular neighborhood of a tubular neighborhood, I get again a tubular neighborhood. Yeah. Yeah. All these are compact. A, B, yeah. All the subsets, yeah. And I can compute also the Hausdorff distance using closed tubular neighborhoods, not just open ones. I think. And more importantly, I can describe the length structure of this space. If I take the distance between two subsets, the Hausdorff distance, I can show that this is actually a geodesic segment. It realizes Hausdorff distance between every pair of its points. Right? So the intersection of these two neighborhoods. And this is quite nice. We'll see afterwards why this plays an important role. Oh, it's Hausdorff. Forward. Oh yeah, this is This is the hyperspace of all compact. So yeah, precisely because of this property, we have that this is compact, and such as compact, and I mean, it's just a matter of a computation to check that this is never empty, this intersection. So this is, and then to check that it actually realizes the Hausdorff distance. Okay, so like a very super trivial example. If we take, for instance, two closed balls, which we're interested in storing anyways, well, a tubular neighborhood just looks like this. And it's very easy to compute the Hausdorff distance. Right? It will be just the sum of the distances between the centers and the absolute value of the difference of the rate. And this immediately puts our attention in a particular kind of metric space. Is the taxi cab. So whenever I have two metric spaces, I can hook up this taxi cab product just this way, right? So I can see here that this is a taxi cab product of real numbers and the metric space. We'll see. This is called like driving in Manhattan. Yeah, exactly. It's like the Manhattan metric or whatever. So yeah, just actually the picture, right? So we have the taxi cab metric. Given any 2 points, they can be joined by one of these taxi cab routes, right? And all of these paths are realized this time. Right? So we have a problem. I mean, contrary to what we have seen when we consider metric measure spaces, here we always have this behavior that we don't like, the branching of geodesics, right? And it's precisely because of that. Right? There are several, actually, could be even infinitely many geodesic segments joining every pair of points. Oh, sorry. If I can extend any one of these paths, we will have the geodesic branching. In particular, and this rules out the possibility for this space to have any curvature bounds, right? Even for below or above. So actually, this property of being able to extend any geodesic segment into a geodesic ray turns out to be rather important, right? So we gave it a definition. We call it just strong geodesic extendability. Okay. So going back to business, I mean, this was the interlude. Remember that we were, as a source of inspiration, trying to look at this kind of hyperspace, the hyperspace of all closed balls in one of these locally compact and complete length space. So now we endow it with this I mean, we've seen that this is actually the distance between two of the closed balls. So we can have this function here between that assigns to each ball center at x and radius r, this point rx, that is on this Cartesian product. And this is precisely the taxicab metric here, right? And what we have shown is that this turns out to be an isometry if this property of a strong geodesic extendability, not inextendability, extendability, holds on X, right? So we have this isometry, right, as metric spaces. So further, if we ask for something else, if we ask for the existence of unique midpoints, I mean, there will always be midpoints, but now we ask them, impose them to be unique. We have this phenomenon, the isometric rigidity. That is that when we consider our hyperspace, its isometric group is precisely the isometric group of the original space. Right? And clearly, every isometry here lifts to an isometry in the hyperspace. But what is interesting and important is to show the converse, right? And that can be attained using the geodesic extendability and existence of unique midpoints, right? Well, if you recall, what we show is that as motivation was that something similar occurred in the larger class of all compact subsets, right? We have a description for the hyperspace, and it was precisely the same description for the Gromov-Hausdorff version of it, right? So the next step is going and tackle this issue, and we are making good progress. We have a partial description. Remember, in those other cases, the Hilbert cube appeared. So here, the Hilbert cube is also appearing. So, but we just need to check some technical details, but we have a description of this. By the way, in the proof of that result of Antonian that described the full Gromov-Hausdorff hyperspace, it is divided in two papers because the proofs are different from dimensions 1 and 2 and from dimensions bigger than that, right? So we are also trying to look at this problem in the perspective of dimension 2. The techniques are different. So this is it. This is the inspiration for what we are going to do. So going back to the original motivation of the problem, to look for examples, we want to have examples of Lorentzian length structures in hyperspaces, and we also want to have this kind of results there, right? To have this kind of descriptions for those hyperspaces that we had already obtained in the, let's say, Riemannian setting, right? So this metric setting, right? So the first construction is the analog. It will be the Lorentzian taxicab product, right? So the ingredients for cook up a taxicab product is to have a Lorentzian length space and a metric space, right? And then we need to define everything that incorporates in the definition of a proper length space. So just if somebody in the audience has not yet seen the definition of what a Lorentzian length space is just a metric space, right? Endowed with two relations. One of them, the causal relation that is a preorder, and a transitive relation containing, and the causal relation is the chronological relation, and a time separation, right? That is just a lower semi-continuous function with respect to the topology generated by that metric, and that that satisfies the reverse triangle inequality. Right? So this is the structure that we want to impose in our Lorentzian taxicab product, right? Well, an example of a Lorentzian length space, just to establish some notation, I will call it just like that. It's the set of real numbers with its regular Euclidean metric. The chronological relation would be just inequality, the strict inequality. The non-strict inequality will be the causal relation, and the positive difference will be the time separation. Right? So this is a perfect example of what a Lorentzian length space is. Okay, so going back to the Taxica product. Going back to the Taxica product, we'll have the Cartesian product as our metric. We'll have precisely a Taxica metric, and then we are going to define the relations. Well, there is not much room to define the relations. If everything needs to work, we'll better have what we expect, right? So in a sense, like the y coordinate, that is what goes in the Lorentzian part, should be greater than the spatial coordinate, shall we say, right? And here is the same. Just we need to make sure that these points are related with the relation in y. And the important part is this, right? How to define the time separation. So this is the definition, right? Precisely the difference between these two. And what we shown is that this is a Lorentzian length space. Computations are quite straightforward. And just to have a concrete example, we can take precisely the Taxica product of this Lorentzian length space, the real line viewed as a Lorentzian length space, and a complete locally compact length space, right? So all the definitions boil down to this, and we have a way to make computation. It's really simple. For instance, if we take X to be just the real, the Euclidean space, the regular n-dimensional Euclidean space, we'll end up with something like this, right? Notice that in this case, the causal diamonds will be as point sets, just the standard causal diamonds, and also the chronological open diamonds, they will be just the same as point sets. But the geodesic structure will be rather different. Like for instance, here, this is the complete causal diamond. And whatever is in this region, on this shaded region, any curve that goes this way from X to Y will actually be a distance, a maximal causal curve, right? Notice that some of them have null segments like this one. All this segment is null, or pieces of it. It obviously contains the unique distance realizing, Lorentzian distance realizing geodesic that exists in the actual Minkowski space will be the straight line segment. But we have infinitely many. As is expected, right? Because this is just what happens in the metric setting, right? So we have the same causal diamonds as point sets, but not the same geodesic structure. Okay. And by the way, just to say, precisely because of this, we won't have curvature bounds in these spaces either, right? Yeah, sectional. Yeah. Or the synthetic notion of sectional bounds, timelike bounds, right? And in this case, in a more general case of having this product, right, the real line and a complete locally compact length space, you can actually have explicit descriptions of maximal causal curves joining any 2 points, right? There are many, infinitely many, but we can pick like nice ones to make computations, right? So given 2 points that are causally related, here T and S are corresponding R coordinates, X and Y are points in the metric space. We take the tau distance, would be like that, and we can make geodesic If it is timelike, a geodesic segment will be given like this. If it is null, will be given like that. And armed with basically this, we can make some computations to show that this will be actually a Lorentzian length space. In general, whenever I have the Taxica product, will be a Lorentzian length space. But if we consider a complete locally compact length space as X, then we can improve this to be a globally hyperbolic Lorentzian length space. As usual, the hardest part is to find the localizing neighborhoods. Well, in this case, it will not be that hard because they will actually be timelike diamonds. And by the way, this will never be regular localizable precisely because we have this geodesic branching. Okay. Another concept, well, so in our quest of finding families of examples, well, there are a ton of them, right? All these Taxica products. Now we have another construction that we had, this uniform product. This will take as ingredients 2 Lorentzian length spaces. We'll have again the Cartesian product, and here we use the uniform metric, right? The uniform metric, and we define the relations. The relations are in each one of the slots, in X and Y, and we define the tau length, kind of taking the rule of thumb that whenever you do something with tau, because the reverse triangle inequality, whatever is a supremum, you take it as an infimum, a maximum becomes a minimum. And just to make it compatible with this distance, we define it to be like that. And it turns out that it will also be a Lorentzian length space. And in this case, we also would like to see under what assumptions we can improve this to make it a Lorentzian length space. So most of the properties translate from each one of the factors to the product, to be locally causally closed, to be causally path connected. But here is something to be very careful. If they are localizable, there is no guarantee that the product will be localizable. So we need to have something stronger here. We need for them to be regularly localizable in order for the product to be localizable. And something similar here. We need to have that there exists timelike maximal curves in order to have our result, right? So if we have 2 that are globally hyperbolic Lorentzian length spaces, then this uniform product will be a Lorentzian length space. If they are regular localizable Lorentzian length spaces, then the product will be a globally hyperbolic Lorentzian length space. So we have here another bunch of different examples, right? So now that we have these general constructions, let's go back to our source of inspiration, that was the hyperspaces. So let's recall, we are considering all compact subsets of a given metric space, but in this case we have more information because this is not only a metric space, it's actually a Lorentzian length space, right? So from now on, we'll assume that the tau is continuous. We need that to make these constructions. And our aim is to find a Lorentzian length structure in this hyperspace, right? So here we have to define as well. We already have that the metric will be the Hausdorff metric. We need to find the relations. So we define it like this. We defined the chronological relation if B is in the future of A and A is in the past of B. It's just a quick reminder, whenever we have points, like this, it's the same saying that Q is in the future of P is just exactly the same as saying that P is in the past of Q, right? But when it comes to arbitrary sets, this is no longer true. Just keep in mind, we have two sets like that. B is in the future of A, but A is not on the past of B, right? So that's why we need to impose both, right? Just to say in quick terms that B is to the future of A. Right? Okay. So what we are about to do now, we have the relations. I mean, these are the natural and obvious relations for this kind of construction. So the tricky part is to find the time separation. So what we're going to do is mimic the construction of the Hausdorff distance, right? So first we need to define what will be a distance from a point to a set, take it into account not a bona fide metric, but instead the tau that we just defined. So this will be the distance. This will be the so-called tubular neighborhoods, right? So, but in this case, again, because of triangle inequality, we need to put the inequalities in the reverse order. And we define the tau in just in the same way, right? It's in this case, not the infimum, but the supremum of all the R's in which these things happen, right? And if we define the tau to be like this, and we have these properties relating the objects that we define, and I just list them here because they resemble somehow the standard properties of the Hausdorff distance. Right? Like for instance, the tubular neighborhood of a tubular neighborhood will not be a tubular neighborhood, but will be contained in a tubular neighborhood, right? And things like that, right? Okay, they're partial analogs of what we would expect in the Hausdorff distance. And well, but it does the trick, right? So the tau that we define in this way makes the hyperspace of compact subsets into a Lorentzian length space. Okay? So this in general. So now we move on to our the point we were most interested in is to look at the space of causal diamonds, right? So we have, in this case, I will demand it to be globally hyperbolic so that automatically the tau will be continuous. And here we have that the set with precisely the relations and the tau separation that we just defined, right? So in order to study this, well, there's another inspirational remark. It's just to observe that in this case, that is precisely the one-dimensional one, we consider as our Lorentzian length space globally hyperbolic the real line. As point sets, the causal diamonds are just the closed intervals, which is the space, the hyperspace that we have studied, right? So there should be some relation in general, we hope, between this hyperspace of causal diamonds and some of the structure that we were able to describe here, right? Remember that in this setting, we were able to see that this is a Taxica product, right? Okay, so as an application, yes. Yes. This is a Lorentzian length space. It's only that. It's Lorentzian length space. And we want to further see what properties do we have in like a particular example, right? And the example that we had in mind is precisely the Taxica product. what will be the causal diamonds in a taxicab product. All right? So first of all, if we have two diamonds well, I can describe a causal diamond by its endpoints, right? And they are given like coordinates, one corresponding to R and one corresponding to the space. So we have two of them, just like in the picture. When one is to the future of the other, like this, that corresponds to basically the initial points and the end and the final points of the diamonds to be related. Right? So this is very easy to compute. Another thing, and this is the most important, is that whenever we have a causal diamond in one of these taxicab Lorentzian space, its tubular neighborhood is again a causal diamond, right? So this is basically what it goes on, right? R will be this little piece here. So whenever we have two different diamonds, we can do what we did in the other case, right? In the regular metric case, we can take the intersection of two tubular neighborhoods. Well, obviously the intersection of two diamonds will be a diamond, right? So in this case, we have the expected result. So we can find distance maximal causal curves joining any two diamonds in the hyperspace. Right? And further, can show that in this particular case, when we consider a locally compact complete length space, this will be a globally hyperbolic Lorentzian length space, the hyperspace of causal diamonds of this guy. And again, the tricky part is the localizing neighborhoods and all the properties that they carry. And again, it will be easy because what we have seen, we can take as localizing neighborhoods just the open diamonds in this hyperspace. Oh, perfect. So what about the inspiration? Remember, the inspiration was that as point sets, this thing is just precisely the metric hyperspace that we have studied, right? So we can make the computations and find the Hausdorff distance between two diamonds and the length separation, the time separation between the two diamonds, and they came out to be these expressions. But if we look closely, this is precisely, since this is a max, this is precisely the uniform distance, and this is precisely the tau distance, well, the time separation is in the uniform product, right? So in other words, if I had a causal diamond, right, I can assign to the causal diamond this pair corresponding to the vertices, and we have this function that goes from the hyperspace of causal diamonds into the Lorentzian uniform product, right? And precisely because these computations, what we have is that this thing is a distance and time preserving map, right? So we also have, I mean, in a way, our intuition was fulfilled. Remember that this guy was a product. In the metric case, this guy was a taxicab. In this case, it will be a uniform product. The image under this map of the space of causal diamonds will be sitting here, right? So, and this is something that is currently being developed. I mean, we just came up with all these ideas like a couple of months ago. The preprint is already in the archive, this one. I mean, the literature is vast, but I'm just point like a very minimal reference. This is our source of inspiration, shall we say. This is when we study that space of hyperspace of compact balls. So this is what we are doing right now. Seminal work on Lorentzian length spaces of continuous Salmon. And if you want to have like a crash course in in hyperspace theory, is this book is very recommended. Right, so this is all I had to say. So thank you very much.